Okay, so let's look at strain. What is a strain? Let me give us a definition for a strain. Now, a strain is the fractional change in dimension of a material. Is the fractional change in the dimension of a material. That is called a strain. And please, it is caused by a force. All right, it's caused by a force. All right, so also a strain can be seen as the ratio of the change of length to the original word length. So it is the ratio of the change of length to the original length of the material. That is strain. Before I give us the formula, I will show us the symbol we use for strain. I will show us two symbols. One is used for compressive stress or tensile, while one is used for shear. Now, the first symbol we use for strain is written as this. Okay, here is the symbol for strain. It's a Greek letter. It is called epsilon. Epsilon. That is the unit for strain. It is called epsilon. It is used for compressive or tensile force. When a compressive or a tensile force is acting on a material or is causing the strain, we use the symbol for strain for compressive or tensile force. All right, but when we have a shear force acting on the material, we use a symbol that you all know very well. It's called gamma. It's called gamma. It's also a Greek letter. This is used for shear force. So when shear force is acting on the material, we use this symbol for strain, for shear force. All right. So these are the symbols we use for strain. Now, as I was saying earlier, I said that strain is the ratio of the change in length to the original length. Now, please, you must note that that change in length is the extension, and we use x to represent that. So I can say that strain as it relates to tensile and compressive force is equal to what? X over L. The x is the original length. Sorry, the x is the change in length. Yes, is the change in length. Or it can be called the extension, okay? While the L is the original length. Please don't forget this. As it relates to shear force, strain is equal to X over L. So we use this for a shear force. We use this for tensile or compressive force. I want us to also note that strain is dimensionless. That means that strain has no unit. Strain is dimensionless. All right. That means that strain has no units. So it can be expressed as a percentage. So we can express strain as a percentage. So sometimes we might be asked to find the percentage strain. Sometimes we might be asked to find the percentage strain. How do we find the percentage strain? So to find the percentage strain, the formula is given us. The formula is given as this: percentage strain is equal to the change in length, which is the extension, over the original length times 100. This is how we find the percentage strain. Question 1. It says, if a wire of length 5.5 meters, that is my original length. So my length L, or my original length, is 5.5 meters. It has a percentage strain of 0.026%. So my percentage strain is equal to 0.026%. Now remember, I have to convert this to a decimal fraction. So I have 0.026 over 100. Okay? That will give us 0.00026. 0.00026. That is my percentage strain. As you know, it has no units. So we are asked to find the extension, which is x. We are asked to find x. All right. So I know that my percentage strain is equal to the extension, or the change in length, over the original length. So I will cross multiply. I have my x, or my extension, is equal to percentage strain times my original length. So what next, guys? I can log in the values. My strain is 0.00026 times my original length is 5.5. So therefore, my extension of the wire, when I put this in my calculator, I should get 0.00143 meters. 0.00143 meters, or I can put it in standard form. It becomes 1.43 times 10 to the negative 3 meters. So that is my final answer. So we are saying that the extension of the wire, due to the tensile force that was applied on that wire, is 0.00143 meters. This tells you that it is very small, that you might not be able to notice it. So sometimes the strain or the extension are very, very small. Okay? So here is a next question, a very simple question. We're asked to find the shear stress and the shear strain. We are told that a rectangular block of plastic material 500 millimeters long by 20 millimeters wide by 300 millimeters high has its lower face glued to a bench. If you don't mind, let me give us a simple diagram of what they are saying. So let's assume that here is the bench. All right. Okay, so here is the rectangular material which is on the bench. All right. Now, we are told that the length of the material is 500, the width is 20, all right, and the height is 300. Now it says, note that the lower face is glued to the bench, all right, so it's fixed. Now it says a force of 200 Newton is applied to the upper face. So a force of 200 Newton, for example, here is the upper face, is applied right here, all right, that's the force applied on the upper face of the block. So this is my force right here, and don't forget that the height of this rectangular block is 300 millimeters. Don't forget that. Now it says when a force of 200 Newton is applied to the upper face and in line with it, the upper face moves 15 millimeters relative to the lower face. That means that when this force was applied, there was an extension. So let me use a broken line. When it's applied, there was an extension on the upper face, as you can see right here. So this space here is the extension, which is 15 millimeters, all right, and here is the relative height. Okay, now let us write out the given data. We are given the length of the block as 500 millimeters. Remember, we convert this to meters. It becomes 500 divided by 1,000. That gives us 0.5 meters. Okay. We have the width. The width of the material is 20 millimeters. We convert this to meters, which is 20 divided by 1,000. That gives us 0.02 meters. Then we have the height. The height is giving us 300 millimeters. We convert to meters, we divide by 1,000. And that gives us 0.3 meters. That gives us 0.3 meters. Now, the force applied to the block is 200 Newton. And the extension X is 15 millimeters. So my extension, which is the X, is 15 millimeters. We can also convert these to meters. Becomes 15 over 1,000, and that gives us 0.015 meters. All right, so now I've gotten my given data. The first question is that we're asked to find the shear stress. And I said that to find shear stress, the formula is tau equal to force over area. But what is the area of this rectangular block? Is length times width. So I can say therefore is the force over the area of the rectangular block is length times width. So what next? We log in the values. My force is 200 over the length is 0.5 times the width is 0.02. So therefore my shear stress is equal to 200 divided by 0.5 times 0.02 will give us 0.01. All right, so 200 divided by 0.01 will give us 20,000 Pascal. 20,000 Pascal. And please note that we can convert this to kilopascal. It becomes 20 kilopascal. 20 kilopascal. So that is our shear stress. To get the shear strain, I use the formula gamma is equal to the extension over the length. Now, from this diagram here, the extension is x, which is 0.015 over the length. The length is the height of this block, because that is the it says the upper face moves 15 millimeters relative to the lower face. So the length of this part of the block is 300 millimeters, which we convert to meters, and it gives us 0.3. So it's 0.3. So therefore my shear stress is 0.015 divided by 0.3, and that gives us 0.05. So 0.05. Now we can convert this to percentage. That gives us 5%. So that is our final answer.